morning, one and all. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn about one of the topic in electromagnetic waves and transmission lines as reflection coefficient and standing wave ratio of a transmission line. So before going to derive the mathematical equations for this reflection coefficient and standing wave ratios of a transmission line, let me introduce what is the definition for input impedance. Now from that, how the voltage and current equations are to be written. Then based upon that, we are going to derive the equations for reflection coefficient and standing wave ratios of the transmission lines. So, firstly, input impedance. As the name itself resembles us, that impedance means it is the ratio of voltage to the current, and we are defining here for the transmission line input impedance. Now, from that, it is defined as input impedance of the transmission line is defined as the ratio of the complex phasor voltage to the phasor current at the input terminal of the line. So this is, we need to remember particularly input terminals. So that's why it is said to be input impedance. Generally, the notation for impedance is Z, and for input we are representing it with Z in. So Z in is equal to, it is the ratio of input voltage to the input current, and it is given by V in by I in, which is equal to input voltage to the input current. Our phasor input voltage to the phasor input current gives us input impedance of the transmission line. So, generally, the definition for input impedance means it is the ratio of input voltage to the input current, and now we are defining it for input impedance of a transmission line. Hence, it is defined as the complex form of phasor voltage to the phasor current gives us input impedance, and it should be applied or measured from the input terminals of the transmission line. Now Z in is equal to V in by I in equal to input voltage to the input current, and the two equations, wave equations, solutions of the transmission line are given by V equal to V plus e power j omega t minus gamma x plus V minus e power j omega t plus gamma x. X be the direction of the propagation, and gamma be the propagation constant, and omega be the angular frequency of that wave. Then I is equal to I plus e power j omega t minus gamma x plus I minus e power j omega t plus gamma x. So already we know that these two solutions are obtained from the transmission line equation. Those two are derived as d square v by dx square minus gamma square v equal to 0, and d square I by dx square minus gamma square I equal to 0. Based upon these two are called transmission line equations. Then based upon these two, we'll have the solutions, or V equal to V plus into e power j omega t minus gamma x plus V minus e power j omega t plus gamma x. Similarly, the current equation I is obtained as I plus e power j omega t minus gamma x plus I minus e power j omega t plus gamma x, where gamma be the propagation constant of the transmission line and x be the propagation direction. So basically it consisting of two traveling waves. One is towards forward and another one is towards backward. Okay? Depending upon the directions, we have the arbitrary constants as V plus V minus I plus and I minus, or respectively represents voltage and current arbitrary constants. Now next, so now convert the expressions for voltage and current from source originated coordinate system to the load originated coordinate system of a transmission line. So this can be obtained from, see, let it be, consider one transmission line which resembles the lengths of defining here from A to B is having first conductor, and the second conductor which is having the length of this A dash and B dash, and the input voltage or source voltage which is obtained at the input terminals. Now the is load impedance is connected at the output terminals and is represented with ZL. Okay, so this is the length which is given by, means length between this A dash to B dash is given by the notation as X, and from this load to the source, means this is given by here the length we are representing for the transmission line with L, means where x is equal to 0 and x is equal to L, right? So this is source originated system, and here it will be the load originated system. Basically a transmission line consisting of two conductors. Those two conductors are defined for a finite length with x, and from source to the destination load, these two x values are ranging from x is equal to 0 case, that is located at the source originated system, and at x is equal to L, that load originated system must be connected. Remember one thing, always this load impedance must be connected at the output side. So now convert the expressions, means previously what we have voltage, the solution equations from the transmission line, two equations are obtained as V equal to B plus e power j omega t minus gamma x plus V minus e power j omega t plus gamma x, and I equal to I plus e power j omega t minus gamma x plus I minus e power j omega t plus gamma x. These are the two solutions which are obtained from the transmission line wave equations. Now consider these two equations. In that you just replace x by L. See, now convert the given two expressions, voltage and current, two equations from source originated coordinate system to the load originated coordinate system, and by replacing x by L. Means consider these two equations. In that we just replace x by all four places, we are replacing x by L. Then those two equations are to be obtained as V equal to V plus e power j omega t minus gamma L plus V minus e power j omega t plus gamma L, and I equal to I plus e power j omega t minus gamma L plus I minus e power j omega t plus gamma L, where L be the length of the load originated coordinate system of a transmission line, right? So firstly we have to consider transmission line equation. Now from that the solutions two are given as V and I. Now in that all the source originated system x is replaced by L. That L stands for here length of the load originated coordinate system. Now from that, see, we are going to define reflection coefficient of a transmission line. So generally reflection coefficient is represented with the notation gamma, and it is given by, it is the ratio of electric field strength of the reflected wave to the electric field strength of the incident wave. And here we are talking about voltages and currents, means this is resembles with VR to the VI. Voltage at the reflected wave to the voltage at the reflected incident wave. So that is given by, means we are now we are going to derive the mathematical equation for the reflection coefficient of a transmission line. So that gamma equal to VR by VI. Now to define that, first reflection coefficient is defined as the ratio of the reflected wave voltage to the incident wave voltage. That is given by gamma equal to VR by VI. Right? Reflected wave voltage. Generally, the notation for voltage is V, and for reflection, it is resembles with VR. Similarly, the voltage notation is V. For incident wave, it is VI. Now, reflection coefficient is defined as the, in other words, means if you want to consider that is related to the voltages, then it is said to be reflected wave voltage to the incident wave voltage. Now, in place of that voltage, if you want to define it with respect to the currents, then reflection coefficient is defined as the ratio of the reflected wave current to the incident wave current. Means reflected current is represented with IR, and this one is resembles with II. This the ratio of IR to II is also is represented as reflection coefficient in terms of currents, right? So gamma of L stands for here load originated system which is connected at the output, and the gamma is the notation for reflection coefficient. So gamma of L is equal to voltage of backward traveling wave at L by voltage of forward traveling wave at L. Backward traveling wave is nothing but reflected wave, and forward traveling wave is nothing but incident wave, right? Depending upon these two, means reflection coefficient is defined as it is the ratio of voltage of backward traveling wave at the L to the voltage of forward traveling wave at Lth position. Now, depending upon that, if you want to write the previous equation, what V equal to V plus e power j omega t minus gamma L plus V minus e power j omega t plus gamma L. Now, depending upon this one, we are going to write here voltage of backward traveling wave, means this is the term we are supposed to consider it for the reflected. And forward traveling wave means this one is related to the incident wave. Hence, gamma of L is equal to backward traveling. Hence, its magnitude is V minus and the phase function is e power j omega t plus gamma L by B plus is for forward traveling wave and the phase function is obtained e power j omega t minus gamma L. Right? So, if you simplify this equation, then gamma of L equal to V minus by V plus into e power j omega t plus gamma L into e power minus of j omega t minus gamma L. Now, if you simplify this total equation, V minus by V plus into e power j omega t plus gamma L minus j omega t, then minus into minus becomes plus gamma L. So e power plus j omega t minus j omega t gets cancelled, which is equal to V minus by V plus into e power gamma L plus gamma L gives us 2 gamma L, right? So gamma of L is equal to V minus into e power j omega t plus gamma L by V plus into e power j omega t minus gamma L, which is nothing but V minus to the V plus into e power 2 gamma L, where V minus and V plus are the magnitudes of backward traveling wave and the forward traveling wave respectively, and gamma be the propagation constant into the length of the transmission line at the load originated coordinate system, right? So gamma of L is equal to V minus by V plus into e power 2 gamma L. Now consider this as equation number 1. Now, V of L is equal to, so previously what we have written, V equal to, the solution for the transmission line equation means we have considered that V equal to V plus e power j omega t minus gamma L plus V minus e power j omega t plus gamma L. Now we are talking about the length. L is to be load originated system transmission line, hence V of L. In place of V, we just consider here V of L equal to V plus e power j omega t minus gamma L. This is for forward traveling wave, and V minus into e power j omega t plus gamma L is for backward traveling wave. Now consider that as equation number 2, and from the reflection coefficient, what we have defined according to the previous statement, reflection coefficient of L is equal to, it is the ratio of backward traveling wave to the forward traveling wave. So V minus into e power j omega t plus gamma L by V plus into e power j omega t minus gamma L. Now cross multiplication between these two means gamma L is multiplied with V plus e power j omega t minus gamma L, which is equal to V minus into e power j omega t plus gamma L. So gamma of L into V plus e power j omega t minus gamma L equal to V minus into e power j omega t plus gamma L. Now consider this as equation number 3, another relation. Now by substituting equation 3 means gamma of L into V plus e power j omega t minus gamma L equal to V minus e power j omega t plus gamma L. So this is the term which is existing in the equation number 2. So in place of this, if we substitute, in place of this equation, if we substitute gamma of L, V plus e power j omega t minus gamma L, then it becomes, means V of L equal to forward traveling wave magnitude and phase function, means V plus e power j omega t minus gamma L plus V minus e power j omega t plus gamma L, means we are substituting gamma of L into V plus e power j omega t minus gamma L. Okay. Then if you take in between these two V plus and V plus as common, then V plus and e power j omega t minus gamma L as common, then rest of the two terms are written as V of L equal to V plus e power j omega t minus gamma L into 1 plus gamma L is left out. Okay. Then V of L is equal to, this is the way we can write. Similarly, I of L is equal to, so this is the equation which we have considered from the V equal to V plus into e power j omega t minus gamma L plus V minus e power j omega t plus gamma L. And similarly, I can be written as I plus e power j omega t minus gamma L plus I minus e power j omega t plus gamma L. So here, if we substitute I plus and I minus y, means in general, the characteristic impedance Z0 can be defined as, it is the ratio of positive, means forward traveling wave current voltage to the forward traveling wave current, or which is equal to minus V minus by I minus. Okay. So now we are considering in place of this V plus as Z0 equal to V plus by I plus. Now from this, if you want to write I plus is equal to, then V plus by Z0. Hence, it can be written as, for V plus, means from this equation, V plus is nothing but, I plus is nothing but V plus by Z0 into e power j omega t minus gamma L minus V minus by Z0 into e power j omega t plus gamma L. Okay. Now, this is another relation. Now, from these two relations, similarly, if we assume reflected current, means previously what we have considered for the voltages, now we are talking about reflection related to the reflection coefficient is related to the currents. So similarly, if we assume reflected current and incident currents, then the reflection coefficient will be negative quantity because reflection current is 180 degrees phase shift with the incident current, right? So that is the case. I of L is equal to minus of I minus, means generally this reflection coefficient can be defined as what, forward backward traveling wave to the forward traveling wave, and it is given by I of L is equal to minus of I minus e power j omega t plus gamma L by I plus e power j omega t minus gamma L. Now, if we substitute I of L, means from the previous analysis, what we have written, I of L is nothing but V plus by Z0 into e power j omega t minus gamma L minus V minus by Z0 into e power j omega t plus gamma L. Okay. Then consider that relation, V plus by Z0 into e power j omega t minus gamma L minus V minus by Z0 into v power j omega t plus gamma L. Okay. Then I of L is equal to, first positive term can be written as V plus by Z0 into e power j omega t minus gamma L minus, if you take here 1 by Z and if you substitute V minus into e power j omega t plus gamma L by this relation. Now we have written in the previous equation, that is if V minus means V minus e power j omega t, V minus e power j omega t plus gamma L can be written as gamma of L into V plus e power j omega t plus gamma L. So now replace these two terms by this term. Then gamma of L, V plus e power j omega t plus gamma L. Now in between these two, if you take V plus, and in both the terms V plus is the common one, and by the denominator Z0 is also a common one, hence V plus by Z0 into e power j omega t minus gamma L into Now, if you take v plus by z naught e power j omega t minus gamma L as common, then the two terms are to be obtained as 1 minus gamma of L. Okay, where gamma is the notation for reflection coefficient of a transmission line. Right? So, the impedance at a position L on the line means in general we can define that is L is equal to, means Z is equal to V by I, or Zn is equal to Vn by In. So like that, the impedance at a position L can be written of a transmission line is Z of L is equal to V of L by I of L. Right? So V of L, V of L means in the previous statement that is V of L is equal to V plus e power j omega t minus gamma L into 1 plus gamma of L, and I plus is here from V plus by z naught in the e power j omega t minus gamma L into 1 minus gamma of L. Right? So in both the places, if we substitute V of L by this relation, numerator part as V plus e power j omega t minus gamma L into 1 plus gamma of L, and in the I of L place V plus by z naught e power j omega t minus gamma L into 1 minus gamma of L. Right? So here V plus and V plus gets cancelled. Thus Z naught is there in the denominator of the ratio, hence it becomes numerator term. Then e power j omega t minus gamma L, e power j omega t minus gamma L gets cancelled. Then 1 plus gamma of L by 1 minus gamma of L can be obtained. So Z of L is equal to Z naught into 1 plus gamma of L by 1 minus gamma of L. Right? So if you multiply these two, means we are going to write the equation for gamma of L. From these two, we multiply, means Z of L into 1 minus gamma of L equal to Z naught into 1 plus gamma of L. Okay. So separate the equation for gamma of L. Hence, we are multiplying Z of L with this total thing and Z naught with this complete thing. So Z of L minus Z of L into gamma of L equal to Z naught plus Z naught into gamma of L. Now we can separate gamma terms and the other terms separately. Then if you take this Z of L into gamma of L to this term, Z of L minus Z naught equal to, and Z naught gamma of L plus Z of L into gamma of L. Right? So in between, this is Z of L minus Z naught equal to, in between these two, this and this as common. If you take gamma of L as common, then it becomes Z naught plus Z of L. Then from that, gamma of L equal to Z of L minus Z naught by Z of L plus Z naught. See here, gamma of L can be obtained Z of L minus Z naught by Z of L plus Z naught. Right? So from these two, if you observe here, if you take Z of L is equal to ZL and gamma of L is equal to gamma suffix L, then reflection coefficient at the position L is given by line, transmission line length. Gamma of L is equal to ZL minus Z naught by ZL plus Z naught. Very, very important one we need to remember. Based upon this, we are going to solve so many problems. So reflection coefficient of a transmission line with a load originated coordinate system means it is given by gamma L is equal to ZL minus Z naught by ZL plus Z naught, where ZL be the load impedance and Z naught be the characteristic impedance. ZL is load impedance. ZL is load impedance. Load impedance. And Z naught be the characteristic impedance. Characteristic impedance. So in general, the impedance notation as Z, depending upon the suffix terms, it is to be termed as load and characteristic. Right? So load impedance is denoted with ZL and the characteristic impedance is denoted with Z0. So for a reflection coefficient of a transmission line, Z gamma L can be given by here ZL minus Z0 by ZL plus Z0. Okay. Now there are two conditions are there how the reflection coefficient is to be varied. if ZL is equal to 0, if ZL is not, if ZL is equal to Z naught and ZL is not equal to Z naught case, how the reflection has to be occur in the transmission lines. So the reflection coefficient at the load end can be obtained. Gamma L is equal to ZL minus Z naught by ZL plus Z naught, which is equal to backward traveling wave to the forward traveling wave of the transmission line, in the transmission line. Now consider there are two cases at ZL is equal to Z naught. First, if we consider at ZL is equal to Z naught, now how the gamma L becomes. Gamma L is equal to, means if you substitute ZL by Z naught or Z naught by ZL, there is no change in that. Why? Because we are assuming at ZL is equal to Z naught as the condition. Now ZL minus ZL by ZL plus ZL. So ZL gets cancelled. Gamma L is equal to 0. So gamma L equal to V minus by V plus equal to 0. So V plus is nothing but incident wave and V minus is the magnitude of the reflected wave. Okay. So gamma L is equal to 0 for the case ZL equal to Z naught. If the load impedance of a transmission line is equal to the characteristics impedance of the line, then there is no reflection occur. So there will be no reflected voltage at the load, right? So, and if the load impedance connected to the line is equal to the characteristic impedance of the line, then the power at the end of the line will be transformed to the load completely, and this condition is said to be matched load, right? So whatever the load impedance is completely whatever the characteristic impedance which is connected at the input side, that should be completely transferred to the load, right? This is the condition called matched load condition. Means ZL equal to Z naught case, there is no reflection. Okay. And one more condition is if ZL is not equal to Z naught, how the gamma L can be changed. ZL minus Z naught by ZL plus Z naught. If ZL is equal to Z naught case, gamma L equal to 0. If ZL is not equal to Z naught case, the impedance abruptly changes from Z naught to ZL and hence the some part of incident wave will be reflected. Okay, that's why see part of the wave will be again reflected back to the same medium. This is the case. The waves are said to be standing waves or stationary waves. So standing waves or stationary waves are nothing but those are the waves which consisting of two traveling waves. One is incident and the other one is reflected, and the two waves are moving in opposite directions. But the magnitudes of those two will be exactly the same. Okay. So at ZL is not equal to Z naught case, part of the incident wave will be reflected to the same medium. This is the case. Waves are said to be standing waves. Okay. So ZL is not equal to Z naught case. Now, so till now we have evaluated that gamma L is reflection coefficient of a transmission line, that is ZL minus Z naught by ZL plus Z naught. Depending upon if the load impedance is equal to characteristic impedance, that condition is said to be matched load, and ZL is not equal to Z naught case, standing waves are to be formed. So what actually standing waves? Then what is the mathematical equation for this standing wave in a transmission line? Now we are going to learn. So the combination of incident and the reflected waves gives rise to standing waves of current and voltage with definite maxima and minima along the line, right? Suppose if we consider one transmission line at the end like this, and distance from the load is considered to be as like this, and if you assume the the load as like this, right? Then this is the distance from the load, end, and This is the current waveform. Current waveform. This dotted lines resembles voltage waveform. See, if you observe these two are moving in opposite directions, right? So here is the means this one is given by here I minimum, and this is given as this length will be given as I maximum, and this dotted lines this one is given by V minimum, and this one as this dotted line's full length will be the V maximum, right? Depending upon V max, I max, V minimum, and I minimum, these waves are to be how the effect will be on the standing waves. Now we will see. So the combination of incident and the reflected waves gives rise to the standing waves of current and voltage with definite maxima and minima along the line. Suppose if we consider the load end which is connected at the L, and the distance from that is obtained as load end is given as like this, and from these two waves, incident and reflected waves, the I max, I minimum, and V max, V minimum positions are to be estimated depending upon the wavelength. So the magnitudes of standing waves provide an idea to the amount of reflection. Depending upon this, the magnitudes of the maximum and minimum of current and voltage on a line having standing wave is called the standing wave ratio, and it is denoted with S. Standing wave ratio is denoted with S. So there are two cases in this standing wave ratio. If you are talking about voltages, then it is given as VSWR, or if you are going to talk about current, then it is said to be ISWR or CSWR. Voltage standing wave ratio, current standing wave ratio. Now we are going to derive the mathematical equation for this standing wave ratio, right? So to derive that, first V max, V minimum, and I max, I minimum are to be derived from the previous standing wave figure. So V max can be given by magnitude of V max must be given by here modulus of Vi plus Vr, where incident wave voltage is given by Vi and reflected wave voltage as Vr, right? So V maximum positions, when we are going to get maximum voltage, means by combining voltages of both incident and reflected waves. And when we are going to get minimum, means the incident wave voltage is subtracted from the reflected wave voltage is subtracted from the incident wave voltage case, right? V max is given by V plus Vr, and the V minimum is given by Vi minus Vr, right? I and R stands for incident waves and the reflected waves. Okay. Now V minimum equal to Vi minus Vr. So similarly, if you consider this as equation number 1, and these two are number 2, see, depending upon V max and V minimum, now we are going to consider here the next two cases as I max and I minimum. So I max is equal to II plus IR, and I minimum equal to II minus IR. So similarly here also I and R stands for incident wave and reflected waves of currents, and I maximum can be obtained by combining both the incident wave and reflected wave maximum positions, and I minimum is to be obtained means the reflected wave current is subtracted from the incident wave, right? So these are the two equations for voltages, and these two are for currents. Depending upon this V max, V minimum, and I max, I minimum, now we are going to write the equation for standing wave ratios. So generally it is denoted with S. Now voltage standing wave ratio, or simply standing wave ratio, is equal to, it is the ratio of maximum amplitudes of the voltage to the minimum amplitudes of the voltage. That is given by, which is equal to, means maximum amplitudes of the wave, amplitudes of the wave to the minimum amplitudes of the wave. Minimum amplitudes of the wave. Okay, so that is VSWR or SWR is equal to Vmax by Vminimum. Similarly, current standing wave ratio are simply SWR equal to I maximum by I minimum. Okay, now depending upon that, first consider VSWR equal to. What is the formula for Vmax from this relation VI plus VR, right? And V minimum is nothing but VI minus VR. Okay, by simplifying this equation, we are going to get, see, V max by V minimum equal to 1 plus gamma L by 1 minus gamma L. How it's to be obtained means VSWR equal to V maximum by V minimum of magnitudes is equal to VI plus VR by VI minus VR magnitudes if you consider. So in both the cases, if you consider modulus of VI as common, then it becomes 1 plus VR by VI by, in the denominator also, if you take VI as the common, then 1 minus VR by VI. Okay, so this VI and this VI gets cancelled, which is equal to 1 plus VR by VI. Reflected wave voltage to the incident wave voltage is given by reflection coefficient as gamma of L with the magnitude by 1 minus gamma L with the same magnitude. That is given by here VSWR, or simply it is denoted with small s. Okay, so Vmax by Vminimum equal to 1 plus modulus of gamma L by 1 minus modulus of gamma L, where gamma L is the notation for the reflection coefficient of a transmission line. So VSWR equal to Vmax by Vminimum equal to maximum amplitudes of the voltage to the minimum amplitudes of the voltage, which is given by 1 plus gamma L by 1 minus gamma L, right? And generally we use the notation for VSWR as S, and it is S is given by 1 plus gamma L by 1 minus gamma L. Okay. So previously we have done one relation we have learnt, that is gamma L is equal to ZL minus Z0 by ZL plus Z0, and now we have got S is equal to 1 plus gamma L by 1 minus gamma L. Okay, now depending upon this, now we have a reflection coefficient of a transmission line and the standing wave ratio of a transmission line. So now relation between these two, how we can relate gamma L in terms of S and S in terms of gamma L. So S in terms of gamma L means S is equal to 1 plus gamma L by 1 minus gamma L. Now we are going to define gamma L in terms of S. Means by multiplying these two, 1 minus modulus of gamma L equal to 1 plus modulus of gamma L. S minus S gamma L equal to 1 plus gamma L. Right? Now separate the reflection coefficient as like this. S minus 1 is equal to, if you take S into gamma L plus gamma L, and if you take here gamma L as common, S plus 1. Now from this, gamma L equal to S minus 1 by S plus 1. This is the reflection coefficient gamma L is obtained in terms of standing wave ratio. So gamma L is equal to S minus 1 by S plus 1. Okay. So similarly, if you substitute, means gamma L, as we know that gamma L is equal to, means as a reflection coefficient gamma L is ranging from 0 to 1, right? Suppose if you substitute gamma L by 0 for the first case here, the ranges of, in order to find the range of the standing wave ratio value. Now first substitute, if you consider gamma L is equal to 0. So S minus 1 by S plus 1 equal to 0 from this relation, then S is minus 1 equal to 0, then S is equal to 1 for the first case. Now, if you are assuming gamma L is equal to 1 for the next case, then it becomes S minus 1 by s plus 1 is equal to 1. Now s minus 1 is equal to s plus 1. Now both sides, if it's cancelled, means this becomes sorry. See, s is equal to 1 plus gamma L by 1 minus gamma L. Now from this we are going to derive the coefficients of these two. Means s is equal to 1 plus if you substitute gamma L by 0 here, 1 plus 0 by 1 minus 0, then s is equal to 1. Now if you are observing gamma L by then 1, then s is equal to 1 plus 1 by 1 minus 1, then s is equal to infinity. Right? This is the way the s is ranging from 1 to infinity. So from these two relations, see, s is ranging from where reflection coefficient gamma is ranging from 0 to 1, and standing wave ratio s is ranging from 1 to infinity. 1 is less than or equal to, s is less than or equal to infinity. Right? So the ranges of reflection coefficient and the standing wave ratios are respectively ranging from 0 to 1 and 1 to infinity. Right? So standing wave ratio, or simply voltage standing wave ratio, gives us here, that is the ratio of reflected maximum amplitudes of the voltage to the minimum amplitudes of the voltage, and it is to be obtained as s minus 1 by s plus 1 in terms of reflection coefficient. Right? So now till now we have learned two topics. One is reflection coefficient of a transmission line as gamma L is equal to ZL minus Z0 by ZL plus Z0, and standing wave ratio S can be obtained as 1 plus gamma L by 1 minus gamma L, or gamma L in terms of S means S minus 1 by S plus 1. Now these are the three relations we have learned now till. Now we are going to learn one more relation, means all the primary constants are expressed in terms of secondary constants. Now what are the primary constants and what are the secondary constants of a transmission line? As we know that resistance or inductance L, conductance G and the capacitance C are called primary constants of a transmission line. Whereas propagation constant gamma, intrinsic impedance means characteristic impedance Z0 are called secondary constants of a transmission line. Gamma and Z0 are called secondary constants of a transmission line. Now we are going to express all the primary constants in terms of secondary constants. As we know that in the previous lectures we have evaluated the equation for gamma, that is propagation constant gamma, as root over r plus j omega L into g plus j omega C. Along with the primary constants, it is also depends on omega, nothing but angular frequency of that line. Okay. Similarly, this Z0 is equal to root over r plus j omega L by g plus j omega C. Suppose if you want to express, means suppose these two are multiplied, gamma into Z0 gives us, what is gamma? Root over r plus j omega L into g plus j omega C, as gamma into Z0 means root over r plus j omega L by g plus j omega C. Okay. Now here this g plus j omega C, this g plus j omega C gets cancelled, which is equal to root over r plus j omega L into r plus j omega L. Now if we multiply these two, root over r plus j omega L whole square equal to gamma into Z0. The square and root gets cancelled, then r plus j omega L is equal to gamma into Z0. Okay. Now one more relation. Now if you want to multiply these two, multiply means r plus j omega L equal to gamma into Z0 has obtained. Now if you want to divide these two, gamma by Z0. Now what is the gamma here? Root over r plus j omega L into g plus j omega C by z naught root over r plus j omega L by g plus j omega C. Okay. Now if you divide these two, means if you want to evaluate this one, r plus j omega L into g plus j omega C, right? Root over into. In the denominator we have the ratio, means this becomes root over g plus j omega C by r plus j omega L under root itself. This g plus j omega C and r plus j omega L means this and this gets cancelled, then root over g plus j omega C whole square is to be obtained. This square and this gets cancelled, which is equal to g plus j omega C as gamma by z naught equal to g plus j omega C, right? So now in the similarly, if you want to write z naught by gamma, reverse case, then it becomes 1 by g plus j omega C. Okay, this is the way we have got all the primary constants in terms of secondary constants. Okay, gamma into z naught is equal to r plus j omega L and z naught by gamma equal to 1 by g plus j omega C, or gamma by z naught equal to g plus j omega C. Okay, so what we have learnt in this particular lecture is the reflection coefficient of a transmission line and standing wave ratios of a transmission line, along with that calculation of primary constants in terms of secondary constants, right? So we have learned this reflection coefficient gamma. It is defined as is the ratio of backward traveling wave at the position L to the forward traveling wave at L. And depending upon that, we have considered two voltage and current equations as V equal to V plus e power j omega t minus gamma x L and plus V minus e power j omega t plus gamma L. Okay. And current equation I can be obtained as I equal to I plus e power j omega t minus gamma L plus I minus e power j omega t plus gamma L. Depending upon these two equations, means these are the two solutions which are obtained from the transmission line equation, that is d square v by dx square minus gamma square v equal to 0 and d square I by dx square minus gamma square I equal to 0 are called transmission line equations, right? So the solutions are given by here v equal to v plus e power j omega t minus gamma L plus V minus e power j omega t plus gamma L, and I equal to I plus e power j omega t minus gamma L plus I minus e power j omega t plus gamma L. Depending upon these two, we have considered the maximum amplitudes of the voltages and minimum amplitudes of the voltages. Along with that, we have written means reflection coefficient at the load is given by it is the ratio of ZL minus Z0 to the ZL plus Z0, where ZL is the notation for load impedance and Z0 is the notation for the characteristic impedance. Now, in this case, we have evaluated two conditions. The first one is if ZL is equal to Z0, and second case we have evaluated is ZL is not equal to Z0. If ZL is equal to Z0 case, whatever the power which is transmitted from source originated to the load originated, that is completely transferred from source to the destination. Means this is the case. The load line is said to be matched load line and the condition is called as matched load condition. If ZL means there is no reflection occur in this particular case, ZL equal to Z0 case. And the second condition, if ZL is not equal to Z0 case, the part of the incident wave is reflected back to the same. Depending upon that, standing waves are to be formed. There are two cases are there, that voltage standing wave ratio and the current standing wave ratio. Means it is the ratio of maximum amplitudes of the voltages to the minimum amplitudes of the voltages or maximum amplitudes of the currents to the minimum amplitudes of the current. Depending upon that, the notation which is given for the standing wave ratio as S, and it should be written in terms of reflection coefficient as S is equal to 1 plus mod gamma L by 1 minus mod gamma L, and from the reflection coefficient gamma L in terms of standing wave ratios means gamma L is equal to S minus 1 by S plus 1. Okay. Then followed by, we have learnt all the calculation part related to the all the primary constants in terms of secondary constants. As we know that resistance L, resistance or inductance L, conductance G, and the capacitance C are called primary constants of a transmission line, and propagation constant gamma and the characteristic impedance Z0 are called secondary constants of a transmission line. Depending upon that, gamma into Z0 gives us R plus j omega L, and gamma by Z0 gives us G plus j omega C, or Z0 by gamma gives us 1 by G plus j omega C. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.